Dear students, in this video, we will continue our discussion on characteristics of matrix or how we can characterize matrix using a few numbers or few vectors. In last video, we learned or had a quick revision about determinants, and we learned that determinants can tell us a lot about that single real number that can serve as mapping for a real valued matrix. And in this video, we are going to talk about two topics that often haunt us the most, what we call as eigenvalues and eigenvectors. And we will try to make these two concepts as intuitive as possible. Now, whenever the word eigenvalues come in the mind, we are typically used to think about that ax equal to lambda x, and that would mean that multiplication of a matrix by a certain vector would result in some scaling as if we are multiplying that particular vector by some constant. But the question arises, what is its geometrical significance? How it can be related to our discussion on basis and transformations that we had before. And this is what we will try to uncover in this particular lecture with help of a few concrete examples. Now, let us try to understand the meaning of this equation, how it comes into existence. To know that, we will define what we call as the characteristic polynomial. Mind it, this is the definition. So, definition says that characteristic polynomial can be written as determinant of a minus lambda I, and whenever we take the determinant of this particular equation, if this is an n cross n matrix, if A is an n cross n matrix, we would be essentially solving for n roots, and whenever we solve for those roots, the solution of this equation, whenever we equate it to 0, it represents the eigen values. So solving this equation, getting n roots, some of them would be distinct, some of them would not be distinct, but at the end, this is the equation or the definition that gives us the eigenvalues in a given system of matrices. Now, if this is clear, let us go a little bit more geometric and try to understand what eigenvalues would mean for a real vector. Let us consider a Cartesian coordinate system and a vector whose coordinates are given by 3, 2. Also, let us consider another vector which is along the x-axis and its coordinates are given by 1, 0. We introduce a transformation matrix A whose values are given by 1, 1 by 2, 0, 1. Now, when we talk about matrix multiplication or multiplying a particular A with a vector, we learned that we are in most of the cases are talking about the linear transformations or linear mappings. That means either we are rotating a vector or we are stretching a vector. So depending upon this A and the vector that is being multiplied, we will have different outputs. So let us try to see that how these two vectors that we have outlined here react to multiplication with A. Now, if you multiply 1, 1 by 2, 0, 1 by this brown vector that we have written, the resultant vector after transformation, so I will say that it is x phi comes out to be 1 by 2, and here so this has to be 1, 0. This has to be 1, 0. So this comes out to be 1 by 2 and 0. That means we have shrunk this particular vector by a magnitude of 1 by 2. So we have simply scaled this vector if we multiply it by this specific A. Now, if we change the A, the nature of transformation will change. Now, also let us see that what happens to this fate of 3 by 2. Again, if we multiply 1, 1 by 2, 0, 1 by our blue vector represented by 3 by 2, what we will end up with? We will have 3 plus 1, and here we will have 2, which would be equal to 4, 2. That would mean that we are sort of 3 will come to the position 4, That means we are pushing it here and it will stay at the same 2. So we are basically stretching it or expanding it. So if we have multiple vectors like this in this space, let us represent it by dot, we will realize that all the vectors that lie along our x-axis, they would be simply scaled. That means they would either shrink or they will expand. However, all other vectors which are not falling along these axes, they would look like as if we are shearing them. The points here would shift here, the points here would shift here, and we will see that the if that are we had a collection of vectors that will look like a square, after transformation they may appear little bit sheared as if they have been made to rotate here, and all the vectors along these lines would just shrink or expand. And this is the precisely how we define eigenvectors and eigenvalues. All those vectors which just shrunk or expanded without getting rotated, we call these as eigenvectors of matrix A. As I said, as we change the A, eigenvectors will change. And that is why we say that eigenvalues and eigenvectors are characteristic property of a given matrix. And that is what this word eigen means. Eigen actually means the word characteristic. So this is why these are called as characteristic vectors. And lambda determines the amount by what shrinkage is happening. Amount by which shrinkage happens. And when we combine these two, we understand what these are eigenvectors, and this shrinkage amounts are referred as eigenvalues. And this is our first geometrical notation or notion about the concept of eigenvalues and eigenvectors. Now, once we have learned about this, now this would make sense. That is, if we multiply A by X, it would appear that X is just getting stretched if and only if X is the eigenvector of matrix A and lambda is our scaling amount. The reason I am emphasizing this time and again, because when we go to singular value decomposition or principal component analysis, this concept is going to be very helpful, that what the scaling and non-rotation means in the context of transformations or eigenvalue decompositions. Now, let us also try to learn that what are some of the terminologies associated with eigenvalues and eigenvectors. So let us say if X is eigenvector of A and there is lambda which is associated eigenvalue, it holds that even if we multiply X by some constant C, that means we are talking about the collinearity. That means it was X, Cx could be this total vector, and then even then the eigenvalues and eigenvectors will hold true, as it can be written as Cax, which we can simply write as C times lambda x, because Ax can be substituted as lambda x or lambda Cx. That would mean that if two vectors are collinear, or in fact all vectors that are collinear to X, they would also have X would also qualify to be the eigenvalues or eigenvectors of a particular matrix A. Secondly, let us introduce another term, what we call as algebraic multiplicity. As I mentioned, to determine the eigenvalues, we write Ax equal to lambda x, and which we can write as A minus lambda I times X equated to 0. And we say that, say if either X has to be 0 or A minus lambda I has to be equal to 0. And in case X is not equal to 0 for a non-trivial solution, we would say that determinant of A minus lambda I equal to 0, and it becomes the characteristic polynomial. And if A is of size n cross n, we will have n solutions. Out of these n solutions, some of would be unique, and some of them would be non-unique. So we could have lambda 1, lambda 2, all the way till lambda n, and we see that particular value of lambda is repeating multiple times. Let us say lambda 2 is value associated with lambda 2 is repeating m times. Then we say that algebraic multiplicity of lambda 2 is equal to m. Now, since we have defined this concept of algebraic multiplicity, we can also define the repetitions of eigenvectors in terms of the geometric multiplicity. So again, let us consider that lambda 2 is an eigenvalue and it would have certain eigenvectors associated with that. So one eigenvalue could have multiple eigenvectors associated with that when we solve Ax equal to 0. So these eigenvectors in turn could be linearly dependent or linearly independent. So we define geometric multiplicity is as the number of linearly independent eigenvectors of particular lambda 2. Now, this linear independence of eigenvalues and eigenvectors also help us determine the dimensionality of subspace spanned by eigenvectors associated with lambda 2 specifically that we are talking about. So to understand these concepts, let us look at one simple example and try to put all the concepts that we have been talking to justice. So let us consider a matrix A represented by 4, 1, 2, 3, and we are supposed to find its eigenvalues, eigenvectors, vectors, values. Also, we will obtain the eigenspaces. Eigenspaces is that the subspaces that are spanned by the eigenvectors associated with each lambda or each eigenvalue. So first of all, we will go with basics. You can always do all these things on computer, but it is always good to develop some intuition by solving some examples by hand. And when we have A, using the definition, we can always write determinant of A minus lambda I equal to 0. That would mean 4, 2, 1, 3 minus lambda 0, 0 can be written as 4 minus lambda 2, 1, 3 minus lambda. So when we factorize it, we can write this as 4 minus lambda into 3 minus lambda minus 2 equal to 0. As we said, we will solve the roots of this equation. Upon expansion, this becomes 10 minus 7 lambda plus lambda square equal to 0, which can be written as 2 minus lambda and 5 minus lambda, which implies lambda equal to 2 and lambda equal to 5. You see that lambda equal to 2 is only appearing once, hence the algebraic multiplicity of lambda equal to 2 is 1. So is the case with lambda equal to 5. Now, next task is how we can find the eigenspace or eigenvectors associated with a particular lambda. So now, if we substitute lambda equal to 5 in our original equation, we can write Ax equal to lambda x, and we have determined a lambda. So if we bring it here, we can always write A minus lambda times x equal to 0. So if we substitute lambda and subtract it from A, it becomes 4 minus 5, 1, 2, 3 minus 5 multiplied by x1, x2 equal to 0. And when we look at this equation, we have already learned about solving this system of equations by converting them into row echelon form and then looking for the pivot columns and then representing non-pivot columns as the linear combination of pivot columns, and that will give us the solution of our Ax equal to 0 form or all general solution. And in this case, I will not repeat that, but leave it to you that how you can determine E5 as span of 2, 1. That would mean that the eigenvectors associated with lambda equal to 5, they are 2, 1 and all the collinear terms. That means if you multiply it by 3, 4, 5, 6 and so on, does not matter. They are still collinear and hence all would classify to be called as eigenvectors of particular matrix A. Similarly, when we look into lambda equal to 2, we can find the solution as 4 minus 2, 1, 2, 3 minus 2 multiplied by x equal to 0. And when we solve it, we get the solution as 1 minus 1. So E2 would have the span of 1, 1 minus 1. So the subspace that is spanned by 1 minus 1 is also called as eigenspace. Another fancy term for a very simple concept that we already learned when we were talking about spans and bases. In this case, you see that the geometric multiplicity of for all these vectors, they are going to be 1 because they are only one single vectors that are spanning that particular space.